Okay, guys, welcome. Thank you, whoever liked my wallpaper. I just saw that. It changes every day, actually. Fun fact, I have like a bajillion images in there, and they're all things that bring me joy for a different reason, and I put them in there. So I like when you guys tell me you like my wallpaper. I'm flattery will get you everywhere, okay? So, good morning. Couple procedural things before we go through our questions, okay? So I'm gonna pull up Canvas for just a second. If you notice, I kind of restructured a little bit based on student feedback. So couple things. One, you should have done one already here. What should we have done already? Hit the space bar, everybody shout it out. What should we have done?
Attendance link.
The attendance link. Everyone should have done the attendance link already. If you have not, it is right here. Please do it. You already found your Zoom link, so that's good to go. If you're ever absent, there will be a version of a Zoom recording for the class that you missed, okay? It may not be your specific class period. It may be Mr. Williams or myself. We're the two that record, okay? So it'll be a version of a class, and you will get the content everyone else did. A lot of you guys have been like, I'm absent and I don't feel like I'm learning. I'm like, well, have you been using the virtual lessons? So like, see here, there's a bunch of recordings in a folder for you, okay? You got stuff. See, Mr. Willis did the last one. So for this, next, I restructured the module because Unit 1, we were very lax with due dates, and I didn't give anybody late penalties. I think y'all noticed that like, oh, I turned this in 5 days late, whatever, I got full credit, right? Since the system is now in place, we're in our 5th week of school. We know what's going on now. We know how to get into Canvas. All those procedural things are out of the way. Late grades are starting with Unit 2. Late grades are starting with Unit 2. Late grades are starting with Unit 2. Okay, so we are in Unit 2, and therefore what is starting? Everybody.
Late grades.
Yes, I know y'all are rolling your eyes at me, but someone is going to email me going, Miss, I didn't realize late grades were a thing now. Can I have a break? And I'm going to be like, dude, you got like 4 weeks of breaks, like so many breaks. All the breaks are gone. We don't have any, like if we were breaks, we wouldn't even be a Kit Kat anymore, okay? So we are doing late grades. I adjusted the text headers to make it easier. Now, I used the weekly learning plan, I went through it, and I organized the text header so there are no questions. Everyone here is B day. So as you see here, B day, this was supposed to be done prior to class today. These are the notes. It literally says it in the text title, okay? Asynchronous activities that are due by 11:59 p.m. tonight are right here. So you have the weekly learning plan, and you have the text header screaming in your face, like, bah, it is due today, due today, due today. There's no option for telling me you didn't know when it was due, okay? If you can get in Canvas, you know when it's due, okay? So you have to do one of each of these. Remember, we have the learning menu style. You can pick one, but you gotta do one. If you wanna retake the Unit 2 test, what do you think I'm gonna say? You have to have all of these done, right? Just like Unit 1, so I would do them now, okay? They have to be completed or you can't retake. For those of you that already showed up to tutoring, thank you so much for coming. We had a great session discussing everything. Next tutoring is tomorrow, 3:30 to 4:25. You have to log in. If you log in before 4:25, I will stay later, but I'm not gonna hang around at the school till 4:45 hoping someone comes in Zoom. Right? That's not going to be a thing. I have kiddos myself. So you got to log in by 4:25. You're all at home, right? So you have nowhere to be. Log in by 4:25. Okay? That's the end of the school day. All right. So all of these due dates are here. See, due prior to class next time. This is what you have. Asynchronous. This is what you have. I went straight off the weekly learning plan. I put the learning focus titles down here still. I just moved them down so you can know what we're doing in this unit, but there's nothing underneath them because I didn't want it to be confusing because there was multiple due dates and multiple learning focuses. Does this make more sense to you guys? I tried to do it based on student feedback. So this is what you guys asked for. So this is what I'm doing, okay? So thank you to everyone who was brave and asked me to redesign it because I appreciate the feedback on making this a good experience for you too. So don't be afraid to give me feedback if you have it. Any questions? What's starting now in Unit 2?
8th grades.
Yeah, I know y'all are laughing, but someone is going to email me and I'm gonna be like, it's you. You're the reason I said that. Okay, and it's gonna be hilarious. All right, so moving on, I had a question for you guys in the beginning of the class. I asked, how do you identify a family in public? So I'm going to use my name picker, which I already have open because I am on top of it today. Boom goes dynamite. Okay, let's see. Dun, dun, dun. Load, please. Load, please. 6th, and click. Sia. Sia go saying, Sia. Sia G.
Hi.
All right. How do you identify a family in public? Like you are at the mall, Fairview, Galleria, whatever's your jam. How do you identify a family?
By how many members are in the family? Like how
Yeah. Yeah, if it's a field trip, it's obviously not your whole family. No one has 20 kids, right? So good. So there's a number of things. How else? I'm going to pick on so many people today. It's going to be so great. Y'all are going to do so much talking. Dia.
Hello.
Hello. How do you identify a family in public?
If they're like grouped together.
Yeah, they're grouped together. They're close in proximity, hopefully, right? Hopefully. They're not like little kids. My kids run and hide underneath clothing racks and it drives me crazy. But most families stay together, right? Unless their kids are cray-cray like mine. Okay, good. So they're in close proximity. Let's see. Victoria, what's another way we can identify a family in public?
They share similar characteristics.
Yeah,
Physical or personality-wise.
Oh, you said personality. Gold star. You did 2 in 1. Twofer, and I didn't even pay you. Okay. So they may look the same. You might have similar noses, similar skin color, depending on the skin color of mom and dad, hair, etc. Like both of my kids have my blue eyes, but they both have their dad's nose. So like I can see both of us in their features, right? Also personality. Like if you've watched My Big Fat Greek Wedding, and there's like the crazy Greek family and the really reserved British family. That's a really old movie, so I understand that's a really outdated reference, but it is funny if you ever want to watch it. But families behave differently. So you inherently understand what I mean when I say the word family, right? It is the exact same thing in chemistry. Like, exactly. We identify a family by elements that are grouped together on the periodic table. So they're in close proximity for a reason. And we're going to talk about why when we do electron configurations later, because electrons are what determine personality. But they all behave similarly. Okay. And they're grouped together. And they look similar, as in their electron configurations look similar. So visually, if you could see the electron configuration, it would look similar. So I'm pulling up ptable.com. If you do not have this booked, please book it. This is the best resource in chemistry going, because periodic table is like, if there was a religious text, if chemistry was a religion and we had a Bible, it would be this, right? The periodic table is what guides everything in chemistry. You will get so sick of seeing it, or you will love seeing it. It's kind of wonderfully beautiful in how it's arranged because there's a reason. But ptable.com is your best friend. I also have it linked in Canvas. So remember ptable.com, and one of the activities you can choose today has ptable.com in it. Okay, so get familiar. But Jessica, let's see if you watched your notes. You ready, girl? Jessica.
I'm sorry. Did you say my name? I think it's my internet because it keeps saying my internet's not connecting.
Yeah, I said your name. Can you hear me now? You can answer me in the chat if you need to.
Yeah, I can hear you now.
Okay, awesome. Who organized the first periodic table?
Dmitry Mendeleev. I don't know how to.
Mendeleev, yes,
That's his last
Dmitry
name.
Mendeleev. Dmitry, some Russian guy, right? Not Dmitry like the little bat in Anastasia, which is super cool. But Dmitry Mendeleev, okay, he organized the periodic table first. He realized there was a system and things repeated. The word period, periodic. If I make bad jokes periodically, it means I make them repeatedly, right? With spaces of time or whatever in between. The properties of the table happen repeatedly or periodically. So that's where he got periodic. And then table because it's a table, right? So Mendeleev did the periodic table. How did he choose to arrange it? Maheen, how did he choose to arrange it?
Is it by atomic mass?
Yes, he weighted it by mass. So if hypothetically, if this was people, this would be like me having you guys come in the door, stand on a scale, order you guys from lightest to heaviest, and sit you down in the classroom arrangement. So that's the idea of Mendeleev. Mendeleev would have embarrassed everybody on a scale and made them sit on the table based on their weight, right? So that's Mendeleev. Mendeleev is mass, okay? Who was the next guy that was like, nah, dog, there's a better way to do this? Trisha. Trisha, Bobisha, Banana, Fana, Fofisha. Are you here? Let's see.
Yeah.
Yeah, you are. Hi. Who was the next guy? You're muted, baby, if you're trying to talk. Or you might not be trying to talk. I'm not sure.
I think it's Henry.
Yep, that's the guy, Henry Moseley, right? Moseley. So Moseley decided that the number of protons, or the atomic number, is what we should organize them by, because the atomic number decides what it is. It's the DNA. It's analogous to the DNA of us. It decides the identity of the atom. So he was like, okay, atomic number is much better, because some of these masses, because of the amount in the nucleus, are putting it so the electrons and the families aren't staying together. So this allowed the families to stay together, because that electron shape, the electron orbitals, are what decide personality. So we had Mendeleev, and what did he do it by? Everyone can hit the space bar to say the word. Mendeleev was by?
Atomic mass.
Yes, mass. And what was Moseley by?
Atomic number.
Right. Moseley was number, okay? So if you can have that, that's good. This is the Moseley version of the periodic table, okay? Scale of 1 to 10 in the chat, how we're tracking so far. 10 means like, I got Moseley, Mendeleev all day. And then 0 means I don't even know what we're talking about. What's chemistry? Beautiful. I love all those high numbers. Remember, if you want to tell me a lower number and you feel a little like embarrassed, please send me that number privately, and I still want to see it, because I need information. I cannot read your brain. I think I also told you I do not want to read your brain, but I can't do it either. So, okay. All righty. So, who's next? Kiera.
Hi.
Hi. Tell me everything you remember about the alkali metals. I have highlighted the family on P table so you can see what I'm talking about, but tell me everything you remember.
They're metals first.
Yes,
And
metal, good call.
they're malleable and ductile, and they can also conduct electricity.
Yes, they're ductile, they conduct electricity. They're malleable, as in you can change and move it around, right? Like Play-Doh is very malleable. And they conduct electricity. The one that you missed that I'm going to show you guys, because it's super cool, is that it's highly reactive in water. So I'm not going to do the sound. The sound doesn't really matter much. It's a bunch of very bumpkin sounding people throwing things in lakes and watching it explode. But here we go with sodium. So this is what sodium looks like. See how it's white and it's hard. It's hard. It's like chalky kind of. See how it breaks apart like chalk? It's brittle. Okay. Very brittle. But the coolest thing about sodium is that it's super reactive in water. So they're all like arguing about who's going to throw it in the water, right? So they walk over there. So they're going to throw a chunk of sodium about this big. So think like a softball sized chunk of sodium in a pond, and we're going to watch what happens. Okay. We're going to watch what happens. Again, this is a jinky video, but it's one of the best ones I've seen. So, all right, let's see what happens. You going to throw it in the water? It's really bad cinematography here. Tosses it in. Okay. Starts to smoke a little. Blam, right? So When I say that alkali metals are reactive, this is what I want you to think of. They are reactive. They are explosive. They are more explosive than Kim Kardashian, okay? Like they are ridiculous, okay? They interact with water. So when they get exposed to water, highly reactive, that's how they happen. So when you're looking at alkali metals, think highly reactive, water explosions, kind of chalky. It's like if you threw your sidewalk chalk in the water and it exploded. Like that's basically the idea of what it looks like and what it does. Obviously sidewalk chalk is not sodium, because if you touched it and your hands were wet, your hand would explode. But just that's the feel of it, if that makes sense. So you can have a picture to text, like to like texture to attach it to, okay? Normally I'd let you guys touch things in here and I had a whole texture thing, but you know, we can't touch things now because COVID, so that's cool. Lucas, you are the next one it selected, okay? Lucas, tell me everything you remember about alkaline earth metals.
Not that much actually. I don't really remember that.
That is okay. Do you have your notes in front of you?
I can't find them.
That sounds like a great situation. Okay, so if you need help finding the notes or if you need help printing them, let me know, okay?
Okay.
So I'll walk you through. So if alkali metals and alkaline metals have similar names, they have similar properties, okay? So the easiest analogy way to remember this is like when I was younger, we said like people of the earth or like the hippie people, right? Hippie personalities. I'm kind of like a pseudo hippie myself, okay? So hippie personalities are very chill, right? Go with the flow. So alkali earth metals are like the chilled out version of alkali metals. They're reactive, but they don't explode, right? They're just like, not worth exploding, right? They're more level, but they will still react. They'll still react to things, but they're a little more chill. They're also that shiny. They're not going to be as brittle, but they're shiny and malleable, things like that. Okay, so it's the chilled out version of alkali metals. So alkaline earth metals. Oh, where did the pictures go? I had them pulled up. What did I do? Past me is such a jerk, guys. Okay, here it is. All right, so here we go. This is what alkali earth metals look like. Okay, beryllium, see how it's shiny? Kind of looks like what you think a metal looks like. So just to give you a mental picture, these are earth metals, okay? They're a little bit, they will react, but they're not as reactive, okay? They don't have as big of a deal, okay? Let me see, who am I gonna call on next? Sonali, hello.
Hi.
All right, tell me everything you remember about these transition metals. Oh yeah, if you click on them, guys, it gives you answers too. That's pretty cool. Tell me what you know about transition metals. Anything.
They're solids.
Mostly except for which one? Which one's not a solid? It's in thermometers.
Mercury.
Yep, but the rest of them are solids. Okay, go ahead.
Are they reactive?
They are reactive and they're really good at conducting a couple things. What are they really great at conducting?
Electricity.
And heat, right? So copper is in a lot of wiring in houses, right? And that's why in old abandoned houses, like if you grew up in D-Town, like I grew up in Detroit, right? So a lot of times when houses were abandoned, people would go loot the house, but they would rip the wires out of the walls because copper is expensive, but it's also what is used in most wires, a great conductor of electricity. So my super ghetto example helps me remember. But the gold, the copper and things like that are great conductors of electricity and heat. The alkali earth metals and the alkali metals are great conductors of electricity, but marginal conductors of heat, okay? So if you conduct electricity and you do not see conduct heat, then it isn't a transition metal. Transition metals are great at conducting heat. Hold on. Admit, sorry, someone's trying to get in. I got totally distracted by the, so there they are. Hello, welcome back. So transition metals, great conductors of heat and electricity. They're malleable. They're usually solid except for mercury because, you know, liquid in thermometers and things like that, okay? Metalloids are elements that have properties of both metals and non-metals. So I want you guys to take a look. alkali metals, alkali earth metals, transition metals, post-transition metals, metalloids. These are all metals. So that's like 80% of the periodic table. The types of elements, most elements are metals, okay? Like rock on, heavy metal, like Ozzy would be so proud, right? Most of the table is Ozzy Osbourne, all right? The only two that are not non-metals that we are discussing, I'm gonna qualify that we are discussing, reactive non-metals and noble gases. So basically, reactive non-metals and non-reactive non-metals. So I have a story per usual, okay, to help you remember this. So we have our explosive Kim Kardashians over here, right? Highly reactive, highly volatile, okay? Oh, volatile is the wrong word, highly reactive, okay? Alkali earth metals are reactive and they're kind of a chilled out version, still shiny, okay? Transition metals, we start conducting heat, okay, mostly solids. We have our metalloids, which are starting to transition to some non-metal properties. Our reactive non-metals are things that are not metal, but also reactive, usually in a gas, oxygen gas, nitrogen gas. We see these things. Carbon's not a gas, but these are the reactive non-metals. So a lot of reactions like carbon-based life forms, CHON, CHONPS. All of the organic elements are non-metals. Everything that makes up your tissues, not like the conduction of the hemoglobin and stuff, but we are carbon-based life forms, okay? We're organisms, okay? We're organic. Organic is chomps, CHONPS, okay? Noble gases, so fun, okay? Noble gases, what do you remember about them? Carter, tell me about the noble gases.
They're obviously gases at room temperature and they aren't reactive at all.
Yeah, they aren't reactive at all. This is like when your doctor messes up your ADHD medication and you become a zombie, okay? Like you don't react to anything because every single interaction every other element has is because it's trying to be a noble gas. Noble gases are completely full in their valence shell. You've heard of the octet rule in like 8th grade science. You remember that? They're completely satisfied. It's why the word noble was used. Think these are old dead white guys in Europe, okay? So nobility, kings, queens, bloodlines are what they cared about, right? All these dead white guys. So they named them noble gases because it's like a king, fully satiated, does not need anything, does not react to anything. Like if you're like a small town person with a sword outside my castle saying, come out here, I'm just be like, come at me, bro. I don't care. I got a whole army. I'm not going to react to you. I don't need you, right? They're very aloof. That's the idea. If you give them a personality, it's way easier to remember. Non-reactive, king-like noble gases. They're the cool kids. Everybody was trying to be like the cool kids. A lot like social dynamics. That will help you, okay? So we're going to play a game. I am going to do a what am I statement, and you have to tell me what family I'm in, okay? So Izzy, I know you're first. You're like, gosh dang it. Oh. Okay.
Hello.
Hello, Izzy. Your internet's much better today. That's very exciting. I know it must be exciting for you. It's much better for you than for us. Okay, you ready?
Yes.
Awesome. You're going to regret that. Just kidding. I am shiny and I conduct electricity. What am I?
A metal.
Good. So now we're going to go more specific. I started off easy, okay? Now we're going to go into specific families. Eden. I am highly reactive, soft, and white. And I conduct electricity. What am I?
Alkali metal?
Yes! Oh, no, say that with confidence. You gotta do that again. Say it with confidence. Go.
Alkali metal?
Yes. Okay, better answer. Even if you're wrong, say it with confidence, okay? Everything you guys say is important. Wrong answers means someone else was thinking it too, and I get the chance to earn my salary and validate my employment. If you're right, I get to reinforce a concept. No matter what you say, it's amazing. So don't be afraid to be wrong, okay? All right, let's see. I am a great conductor of heat and electricity, and I'm malleable. Sangeet. Great conductor of heat and electricity, and a malleable. Sangeet.
I believe that is a transition metal.
And I believe you're right. Confidence, people. Oh, we're gonna do some like when y'all get in here, we're gonna do some superhero poses. We're doing some confidence exercises. You're gonna love it. Okay, it's gonna be awesome. All right. Celine, I don't react with anyone ever. What am I?
Noble gas.
I'm a noble gas. So you guys have this down. So this is the basic of the activities that you're doing today. Give me a scale of 1 to 10 on how you feel about this after going through it. Again, privacy is always an option. Good. Good. I hope you get so good at it, you're annoyed I'm still talking about it. That's the goal. Like if I'm annoying you because you get it, that means you really get it and we're good to go. All right. So we are going to change tacks, okay? In sailing, that means I'm changing direction, okay? Changing directions. We're gonna talk about the atom for a second. Now, I'm gonna remind you before we switch, if we got to the end of that and you're like, I am not the person that's annoyed, I don't get this at all, oh my God, please don't change subjects, and you're like gripping your chair with a death grip, remember, I have tutoring, okay? Tuesdays and Thursdays, if you log in between 3:30 and 4:25, I will stay as long as I need to, but you have to show up by 4:25. Does that make sense? So please don't panic. Come to tutoring. And if those times don't work for you, email me and we'll schedule a different time. Okay? All right. Atoms. Okay, so when you see the history of the atom, I think that everybody teaches it bad because what they do is they show you this and they're like, Dalton did the first model of the atom and it was a solid shape and it was our first idea in the early 1800s, which it really wasn't the first idea. It's not even starting history right. Then they say, then Thomson had his plum pudding model, which no one's even eaten plum pudding anymore, so that doesn't make sense to you guys. You're like, I don't even know what plum pudding looks like, so calling it the plum pudding model literally helps me zero. I might as well be speaking a different language, right? So I don't want you to think about it like this. We're gonna think about it like it's the next Netflix special, okay? And I'm gonna show you why it's kind of dramatic and weird, and I'm gonna take you through some historical concepts where people disagreed on what the atom looked like and how that affected society. Okay, so we're gonna take a little bit of a different tack. Are you guys ready to go on an adventure with me? Is that okay? It's gonna be a little weird. I'm gonna talk a little more than normal, but it's all right. It's normal. So there's most of the main guys that you need to know. You need to know, I know in your notes, like if you didn't notice at the top of your notes, it literally makes statements of what you should know. So the scientists that you absolutely have to know and memorize are in those statements. But I'm gonna show you a little bit more than that for context, okay? Where did it go? I have it in one of these. I need a secretary just to organize my tabs for me while I'm teaching. That's what I need. Can one of you guys get on that for me? Ha, okay. So first, we have Democritus and Aristotle, okay? Democritus and Aristotle. This is in like 400 BC. So the first time people started thinking about, hey, what makes up other things? Like what makes up wood? Wood is made up of something. The first time someone recorded that thought in history that we were able to now read, because we weren't there, it's just anything that's been recorded, we know, right? Was in 400 BC, okay? That's 2,400 years ago. That was the first time, all right? And there were two main schools of thought, two, okay? There was Democritus, okay? He was first, and then Aristotle came shortly after Democritus. They didn't, I don't believe they actually studied together, but they were in the same thinking arena. We've heard of Aristotle, most of us, right? Democritus thought that every object was made up of smaller versions of that object. So if like you had wood, there were like wood particles that made that up. You didn't know about elements and compounds and atoms. None of that was there. So when you see like fabric, there'd be fabric atoms. When there's wool, so that's the idea. Okay, he thought atoms were made of he thought that items were made of smaller versions of that item and they were built up in a certain way. Okay, does that make sense? Thumbs up if you understand. If you're still listening, tell me your favorite food, but don't say anything. Just make the person that's not listening really confused when they look in the chat. Oh, I'm about to eat lunch too. Whew. Looks yummy. Okay. All right. Second, there was Aristotle. So Aristotle is what inspired Avatar: The Last Airbender. Any Last Airbender fans in the house? Like that's one of my favorites, and it's like a family favorite. Like I watched that way back and when it first came out because I'm ancient, and then I watched it with my kids, and now Korra's on Netflix, and it's a very exciting thing. But the whole inspiration for that life and items are made up of elemental energies, fire, water, earth, etc., came from Aristotle. He thought there was elemental energies that made up everything. So we had one guy thinking there was particles, another guy saying, yeah, the particles might be there, but I think the energies is the real deal, right? The elemental energies. So when I said this relates to history, take a look. We're going all the way from 400, 300, 200, 100, going. We are now 1,500 years in the future. It was not until 2,000 years later that anyone recorded anything about what might make up an atom. 2,000 years, people were like, yeah, there's totally wood chunks that are smaller wood chunks and elemental energies, right? And this actually made up the whole thing about apothecaries and miasma. So who knows what old doctor masks look like? Who knows what they look like? Pop off and tell me. If you played Assassin's Creed, these are the guys you buy medicine from.
It was like the bird beak, right?
Yeah. So it looked like this. Okay, my computer's being funky. Hold on. Shimon. So it looked like this. Okay. Did everyone see it? Yeah. So the reason that it looks like that is because they believed people got sick because of miasma, which was an elemental, like an energy, one of those elemental energies in the air that came in. Like when you smelled a bad smell, like rotten eggs, it was really like evil, sick energy you were breathing in, and your brain perceived it as a bad smell. So what they did is they stuffed herbs and flowers inside that beak so they smelled good smells, because they thought good smells would make it impossible for the bad smells to get in your nose and make you sick. So they kept all their herbs and medicines and like flowers and stuff in that beak. And the ironic part that we now understand because COVID, right? And we like as students, you probably think about it more. What just happened to my screen display? Hold on. What's happened to us is that we understand why masks work. So that mask is solid, right? I'm getting the screen to fix while I'm talking. I'm trying to dual, there we go. 1 second. Stupid computers. See, I'm having internet issues too, it's fine. They thought the best I was gonna get, so I totally lost track because that totally distracted me. Hold on. Okay, so those masks worked because it physically blacked their face like this, just like your mask does when you walk around. And by physically blocking their face, they stopped germs from getting in. And they thought of that until they got to germ theory and cells and started disproving it. But there was a large portion of time that that's what people thought happened. Like that was it, okay? After that, let me go back to the timeline. Okay, not this one. My second screen just kind of decided not to be cool anymore. So that's why I'm struggling here. Hold on. I got to find my tab again. It's not that one, not that one. Put all my tabs from both my screens on one screen. I'm so sorry, guys. I know that's really annoying. Here we go. Now I'll share the screen. Now I don't want to project any of your stuff. Zoom, share screen, share this, share it. Okay. So now we have gone all the way through that. Now we have Newton and Dalton. So we talk about Newton because Newton is laws of motion and all objects are moving, like we said, with states of matter, right? So that's why he's mentioned. But then we have Dalton, who's like, you know what? I believe Democritus, and he came up with a couple ideas. One, that atoms are indivisible. So atom means not divided, right? And they are identical. So there's just like an oxygen ball and a hydrogen ball and a nitrogen ball, and they're all the same except they just behave differently. They're just solid and they all behave the same, which we know is not true, but that's what he thought. Okay, so there you are. Okay. So we had Democritus. Okay. And then we have all these other guys. But if you look at the actual periodic table, if you look at the not periodic table, I'm sorry, timeline, take a look at these dates. All of these people were living at the same time, right? They all are living at the same time. So when we present history, a lot of times you think, oh, there was this guy, and then this guy was born, and then this guy was born, and then this guy was born. But what you should really think about it as is like, hey, this is like Kardashian level scientific drama going on, okay? So we have Dalton, who thought it was solid, and then some new data comes out. Some guy does an experiment, right? Who would be the first one? Do we remember who's the first one that thought it came into parts? Who was the first guy that realized there was more than one part of an atom? Letting someone be brave instead of using the name generator, but I will use the name generator. Dun, 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 dun.
Was it Thompson?
It was Thompson. Thank you for being brave. Oh, awesome. Okay. So Thompson came up with the plum pudding model. I know y'all haven't eaten plum pudding. So when I say plum pudding, I want you to think chocolate chip cookie. He thought it was still solid, but that there were electron chips spread throughout it. Okay. Because he realized the different properties and knew there had to be positive and negative portions. Okay. Then more data comes out and another experiment comes out. So this would be like, imagine like they had their version of, if they had a version of like Twitter, they'd be having some Twitter bottles that would like make Trump jealous. Okay. So they would be firing back and forth at each other. Like, well, this data says this. No, this data says this. Well, yeah, this data says this. And they would be posting all their links to their videos and sources and firing back and forth. And it would have been like this huge scientific debate and argument. No, you're wrong. No, you're wrong. And then Millikan comes in with his oil drop. And then this guy does this. So this is all happening at the same time, not at different times. They're all alive. It takes years to publish a paper, years. And back then it took even longer to publish papers, okay? So if it takes that long to publish a paper, if the papers are coming out in the same year, these experiments were happening next to each other. And eventually we got to the point where we realized that as the data came out, certain models couldn't exist anymore. So they won the argument. That would be like the final nail in the coffin of like, yeah, I was the original TikTok poster. Screw you guys. Like that's when they would get there. Does that make sense? So they would be arguing and looking at data until they got to the point where only one model could explain all of the data at that point in time. And it evolved very rapidly over the course of about 5 to 10 years. So we went from 2,400 years of nothing to like 5 or 10 years of very intense study because the technology caught up. We could actually measure stuff. Okay. So all of the assumptions of the world got turned on its head in like a decade. Okay. In less time than you've been alive, the entire scientific world changed. It's crazy. Like the whole field changed. It's like the invention of the internet. Right? Just completely changed everything. So after that, we got to Bohr. And Bohr gave the planetary model. He thought electrons orbited the atom, which we now know they don't orbit like Saturn or like the moon around the Earth, right? But we do know there's a dense nucleus and electrons on the outside. And you get to Schrodinger where electrons may or may not exist, right? The idea behind Schrodinger, the main idea is that if an electron moves at the speed of light, by the time you find it, it's already moved because it's so fast. So once you know where it is, it's impossible to know where it is now. You knew where it was, you don't know where it is. So that's the idea, okay? And once you measure it, it's gone. So it's too fast. That's the whole Schrodinger thing broke down in a very, very, very small piece. But when you guys look at those atomic histories, try to think about it like it is the next Netflix reality drama. Like who would be winning which Twitter battle, right? Who would have made the website to be like, no, you know what? Dalton is dumb and this is why. Like who would have done what? And kind of think of it that way and it makes it a lot more relatable, okay? Instead of just memorizing dates. So that's the main idea I want you guys to get is that scientists are kind of collaborative and argumentative. And now with the COVID stuff, we see that more than ever, right? The scientific community is not in consensus. The arguing you see today over COVID is the arguing they experienced over the atom. Okay, so you actually are the first class I have ever taught that can understand this because of a public debate. other than maybe the vaccine debate, but the scientific community is consensus. The other people are not. So this is the first time the scientific community is completely split in a way that I can show you and I know you understand. Does that make sense? So as we get more data, our modeling for COVID will change, and that is the scientific process. When you see stuff, as in new data suggests this about COVID, new data suggests that, it's because they're taking all the experiments that have been done in that up to that month and then releasing a report. And that will change because people are constantly doing experiments. So it doesn't mean that someone didn't understand or they were wrong or they lied, because I see that all the time. It means that the data is changing. And I'm talking about when scientists are speaking. I'm not talking politics. I don't do the politics thing in class. I don't, okay? But in terms of the scientific community right now, when you see those reports from the CDC changing, it's because they have the most up-to-date reporting. Does that make sense? Like the Cancer Research Institute that I was working for part-time right up until a couple months ago, we would get data from, we would have to publish our data to the CDC, and then they would get a report comparing our data to everyone else's. Does that make sense? So it's a governing body to get all the data in one place, okay? Does that make sense in terms of real world and history? Kind of try to relate the two. Okay, so, all right. We are going to do one last thing, okay? One last thing. I want to show you, it's going to be about 5 minutes, okay? So not much longer, but I want you guys to actually go through the gold foil experiment, okay? There's an interactive, and I'll post the link in just a second, but I'm going to share my screen and show you first. I'm not asking you to watch the video right now. If you would like to go back and watch the video, that is totally up to you. But this interactive, there's a video here about the gold foil. It's pretty cool. You can watch it. It'll explain a lot more about this specific experiment. Remember, this is one experiment that you will have to know. It's one of the objectives. But here, you can actually run the gold foil experiment, okay? That's what it's asking you to do. So when I give you this link, you are going to come to this page. You're going to click Show Graph, okay? Your job is to play with these settings, large and small, clumped or distributed or orbitals or whatever, and then to run the experiment. And I want you to try to get the same numbers that actually happened, okay? So when you look at the gold foil experiment, okay, you're gonna be trying to match your numbers to their numbers, okay? So this is the real experiment and you get the numbers. So you're watching the real experiment, you're seeing the gold atoms. These alpha particles, do you guys know what alpha particles are? Do you guys know what alpha particles are? Anybody who knows what an alpha particle is, go ahead and unmute and show everybody how awesome you are. I'm zooming.
Would those be the protons, neutrons, and electrons, or are those different?
Hold on, guys. Hold on, guys. 1 second. Okay. Oh, nice. Thank you, Matt. Sorry, guys. All right. Can you say that one more time? Because I had to go answer the door. I'm so sorry.
Would those be the protons, neutrons, and electrons, or are those different things?
That's different. So an alpha particle is a certain conformation. Okay, so protons, neutrons, electrons are part of the atom. Okay, but what is an alpha particle?
Is it 2 protons and 2 neutrons that are bound together?
Yes, so it's 2 protons and 2 neutrons bond together. So it's a larger positive particle. So when you see these green guys, you're seeing that a larger positive particle is shooting into the gold foil. And this is what happened. This many passed through, this many deflected, this many reflected. Deflected means that it shifted direction. Reflected means that it came back to you, right? Deflect means to go a different way. Reflect means to come back, okay? So your job is to play with this and run a model simulation and try to get those numbers to match. So when I ran my model, I can already see that these numbers are not matching. So you and your group are going to try to run the model until you get the numbers to match the real numbers. Okay? So what is your goal? What is your goal? Anybody, or I can do the random person. The random generator seems to work better. Let me pick a random person. Eva, what is your goal right now?
To get the numbers to match.
Perfect. I'm giving you guys the link. Make sure it opens, and I'm going to give you guys a couple seconds to get that open before I do the breakout rooms. Okay. And you guys are going to have 5 minutes. 5 minutes. So at 12:22, I'm calling you back. Okay. Rooms are created. You have 5 minutes. All right, guys, welcome back, lovely humans. Spinning the wheel. Charles, did you get the numbers to match? Did you and your group get the numbers to match?
Yes, we did.
Okay, so what did you do? Can you all see my screen? Yeah.
We had a small particle size clumped core with the positively charged particle and distributed for the negatively charged.
Okay, so that got the numbers to match. So here's going to be the tricky question. Thank you, Charles. I'm going to pick on someone else. Running the simulation. Akshar. Good afternoon.
Hello.
Why does it have to be the positive particles in the core and not the negative? How did he make that? Why is that true?
Because they always reflect of the positive particles, so that's why they stay in the middle. And in a model, they also stay in the middle.
Right, but I'm going to rephrase my question a little bit because I don't think I phrased it well enough, and that's on me, okay? So we know that that's the answer, right? But like Rutherford couldn't see this. He didn't have simulation. He saw the data and then made a leap to that assumption, which was correct, like the conclusion. So why is it that the nucleus or the center had to be positive based on the alpha particle behavior? Or you can tell me what you would have seen if the center particle was negative. Either one of those you can answer for me, and I'll leech off of those.
Okay, I guess because the electrons are negative and they're on the outside, so that's why the protons are positive. I'm not sure.
Oh no, I love when you aren't sure. It's wonderful because you know what that means? It means you're thinking and you're trying. So I heard you say things like negative and positive, and your brain is mulching all this information around, trying to come to a conclusion. That's the best thing you can do to learn. So being unsure is a good thing, not a bad thing, okay? So especially when I'm asking open-ended questions like this. So the negative in the clouds, right, allows the positive to pull through it, right? It pulls through, okay? If the nucleus was negative, what would you see? So I'm going to call on someone else. Thank you for being unsure and speaking anyway. Faisal, hello. Faisal, come on. It is your turn. I know you dealt with me yesterday.
The nucleus is negative?
Yeah, what would happen if the nucleus is negative?
The positives would reflect more, right?
Well, would they reflect more or would they reflect at all? Let me do it in terms of magnets. If I have a north and south magnet, what happens?
They would go opposite.
Okay. The north and south magnet are opposites and they attract. Can you put two north magnets together?
No.
No, they repel. So if the nuclei were negative, when the alpha particles hit them, they would stick.
Stick together, okay.
They wouldn't deflect. You wouldn't see deflection or reflection, right? Reflection means you hit it dead on and it's coming straight back at you. Deflection means that the repelling charges caused it to change direction and move away. If they were opposite charges, all those alpha particles would have stuck instead, and you wouldn't see deflection or reflection. It would either pass through because it missed it entirely, or it would stick. So it had to be positive because the two positive charges, if I'm positive and I'm coming towards, and I'm like, I don't like you. It's like when you see your ex in the hallway, right? And you go, oh no, different direction. I'm leaving, right? And that's a joke, but like for real, when you see things that you want to avoid, you change course. That is exactly it. The two positives want to avoid each other, so it deflects. So that's why you know it has to be positive. Scale of 1 to 10, how we feel about that. Okay, that is what I had for you today. Okay, that is what I had for you today. But before you go, I'm gonna ask you a couple questions. Where do you see the due dates for your class? Where do you see the due dates for your class? Shanmati, where do you see the due dates for class?
The
There's headers that tell you, right? There's text headers, and it's also in the weekly plan. So you have 2 places, okay? What is due by midnight tonight, Adhish? What is due by midnight tonight?
The activities.
Which activities? Go look.
The periodic table and then the atomic theory.
Yep, and you just have to pick one. Okay, you just have to pick one. Okay. What is due before next class? Esty, what is due before next class?
Notes.
Yep, the notes, the 2 notes videos, okay? Are there any questions over anything that you would like to ask in front of the whole class? Okay,
So
go ahead.
so we do one from each module, right, for the activities?
Yep, you pick one. So of the activities, so of the ones that say periodic table activities, pick one. Of the ones that say atom activities, pick one.
Okay.
All right. You have no more questions. I will see your lovely faces in 48 hours, okay? Late grades start today.
Thank you.
Yeah, no problem, guys. No problem.